Hey everybody, welcome to our second week of school and our third chapter in the book. We are looking at chapter 12 and we are going to be talking about alkenes and alkynes. So to start us off, let's give some definitions. An alkene is a hydrocarbon. Actually, they're both hydrocarbons. Hydrocarbon that contains one or more carbon-carbon double bonds. Carbon-carbon double bonds. Now, ethylene is going to be the simplest alkene because there's only two carbons, and of course you need to have at least two carbons, and it's going to have a double bond. Ethylene would have the same name as ethane, which would be our two-carbon alkane, but it gets a name change in the ending. Instead of ethane, we're going to make it ethene. Now, ethylene is a common name. It's ethene for the IUPAC name. And acetylene is also a common name, but this will be eth, which we know is two carbons, ethyne for the alkyne, which will have a triple bond. And that's the difference. Alkenes have one or more double bonds, and alkynes carbon-carbon triple bonds. Acetylene being the simplest alkyne. Now we can talk about the Vazquez model with these two. Vazquez model predicts bond angles of 120 for each carbon of a double bond. So bond angles of 120. Whenever carbon is involved in a double bond, it is automatically going to have either two single bonds or another double bond. If it has another double bond, then we would consider that to be linear because it would have, of course, this wouldn't be an alkene because this wouldn't be two carbons, but double bonded carbons are going to be 180 degrees. Now, whenever we have a double bond, just one, we'll see 120 degrees. Now this is again because of the 3 electron groups, and I'll just say here that the bond angles may actually be slightly greater than 120 because of repulsion between groups, especially when these are substituted and we don't have just hydrogens on there. Now, going a little more into the alkenes, let's talk about some of the variations they come in. We get something called cis-trans isomerism. We saw this a little bit in our ring structures for alkanes, and the groups being above or below the ring. If they're both above or both below, we said they were cis on the same side and trans for opposite sides. So with a restricted rotation around the carbon-carbon double bond, an alkene with two different groups on each carbon actually will show this isomerism. So if the two groups are on the same side, if we were to draw a line through our double bond, through the double bond, along the axis of the double bond, as opposed to perpendicular to it. If we do that, I wish there was a way that I could just, like a back arrow, that's what I want. I want a back arrow. It's okay. Then our groups being on the same side means they're on the same side of a line, or they're on opposite sides of the line. So here, same exact molecular formula, but we get cis 2-butene, just to remember, just to kind of go over the naming here. We're going to go over naming in a second, but just to point it out, the 2 in butene, the 4-carbon alkene, indicates that our double bond happens at the number 2 carbon. Same thing here, 2-butene. Now trans and cis, because the groups, the CH3s, that would technically these wouldn't be groups, they're just the rest of the chain, are on opposite sides. Now, when we're naming alkanes, we're first going to name the parent name, or give the parent name to that of the longest chain that contains the carbon-carbon double bond. So we'll give it a parent name. Again, longest chain. And then we'll number the chain from the end that gives the lower number to the carbons of the CC double bond. Lowest number for CC double bond. We'll locate the CC double bond by number of its first carbon. So 1, 2, and so on. Whatever one we come to first will be the number 1. The ending will get an ENE ending to indicate that it's an alkene. And branch chain alkenes are named in a similar way to alkanes that are substituted. And so as an example, I've got a couple of structures here. So let's just make sure we can name these. So if we have a 6-carbon molecule, I don't know why they always number from the opposite side, but you would number from whatever side, or why they always show these opposite. You would number from the side that gives you the double bond first. So 1, 2, 3, 4, and so on, because the number 1 happens to come on this this double bond. And so we would call this hexene because there's 6 carbons, 1 hexene because it happens at the number 1. Now, building on that, the next compound here is still 1 hexene, but now it has a substituent, a methyl group, on carbon number 4. So again, we could number this way, but this would give us the lower number on, well, first we'll treat double bond as a group, as a substituent. So encountering a substituent is the first goal of numbering. You always want to have the lowest number on anything that you can come across. Now in this example, you can see that if we went 1, 2, 3, 4, 5, we would actually get 3 as the first, or as the first number that we come across. It would be 3. Oh wait, but I'm numbering incorrectly there, right? What's wrong with this chain? 1, oh, what's wrong with this chain right here? It doesn't contain the double bond. The double bond has to be part of it. So sorry, I was trying to show you that if you number the other way and you get to a substituent that is also a number 3, just like your alkane, you're going to give it to the thing you're naming. Let me show you what I mean. Okay, so let's say that I have this. Now, if I number from left to right, 1, 2, 3 hydroxyl, 4 alkene, 5, 6. If I go the other way, 1, 2, I get 3 alkene, 4 hydroxyl. Okay, so both of these substituents are going to be on the number 3. Now, which one do we actually call the number 3? Well, in this problem, it's actually easier than I thought, because if we number this way, we give the number 3 to actually both substituents. It's the number 3 for the hydroxyl and the number 3 for the beginning of our double bond. So that's probably the way we should go. But if we were still trying to decide, because it wasn't a tiebreaker like that, like maybe there was another gap in between these two, it depends on what we're naming. If we want to name this as an alcohol, then it makes sense to give the alcohol functional group the number 3. If we want to name this as an alkene, then it would make sure to give the alkene group the number 3. Again, the purpose of naming is to be able to draw these. As long as you can draw the structure in question, the names, you might come up with a couple of different names, as long as you're following rules like if you're naming an alcohol, give your alcohol the lowest number, and so on. So in this case, because the chain starting down here doesn't include the double bond, it doesn't count. So the biggest chain goes through here, and in this sense, the number 2 and the number 3 are going to be our branch points. So we'll still call this 5 carbons overall, so it'll be pentene, sorry. It's 1 pentene as opposed to 2 pentene or 3 pentene. And then it also has a ethyl group and an ethyl group, so we don't have to worry about alphabetical order here. We just say 2,3-diethyl. But again, the only thing that's changing from regular alkanes with substituents is that we have a double bond that we have to specify the position of, and we also have to change the ending to incorporate the ENE. Alkynes have a triple bond, Same naming, only thing that changes is the Y and E. So for this first example, we can see that 1, 2, 3, 4, it's a butene because it's a 4 carbons. Butene, it's 1 butene. And on the number 3 carbon, we have a methyl. So 3 methyl, 1 butene. And over here, let's see, if we numbered 1, 2, 3, 4, 5, 6, 7, then we would be calling this 4 heptine instead of 3 heptine. And well, then we'd also be calling this 2,2. 2,2-dimethyl 4 heptine versus 6,6 dimethyl 3 heptine. Now, why did we decide on 3 heptine? Because this is an alkyne, and so we want the alkyne functionality to be on the lowest number. So we'd rather have it on 3 than 4. So that means we have to number this way and not this way. This might be tricky in the beginning, but you guys will get the hang of it. Let's see. Now, there are some common names that we still use for alkenes and alkynes, particularly those of low molecular weight. So I just wanted to show you some of those. So where we would IUPAC-wise call this ethene, propene, and 2-methyl-propene, common names like ethylene, propylene, and isobutylene still exist. Acetylene is probably the most commonly used common name of the alkynes. Methylacetylene and dimethylacetylene are less common, but acetylene is just ethine, and then you can see the other two there. So don't worry about common names in our class. I'm not into common names. I like the IUPAC names, and so when we're doing any kind of drawings, you should try to do those. Now, give me a sec. Let me open up my book. If I get my book out, I can see if there's a practice problem we can do. Forgive me. My book is in the wrong folder. Alright, so we're looking at chapter 12. Let's see what kind of little examples we can do here. So very quickly, I would recommend for sure that you guys practice drawing some of these from the book, but it says draw a structural formula for each compound. So let's just try 1 or 2 of these. So I'm just going to pick one at random here. Here, this is trans 2-methyl 3 hexene, and maybe we'll draw one and you give me the name of it. Okay. So drawing. So we've got hexene. So let's just get hexene in there. 2, 4, 6. Now hexene has a double bond. It goes to the number 3. Okay, so it doesn't really matter which side we number from. 1, 2, 3, and then we have a double bond. Now, how do I know the double bond doesn't go the other direction? Because then it would end at the number 2 carbon, and we would actually have called this 2-hexene instead of 3-hexene, and that's not the case. So that's not the case. All right. So we've got 3-hexene. Now it says 2-methyl. All right. Well, if this is number 3, then this is number 2. So I'm going to put a methyl group here, which makes this right here an H, because every carbon is going to have other carbons. I'll just show you your carbons. Right? These are our carbons, 6 of them. There's a CH3 up here. And then we have an H, and then it says that this is trans. Now here's where I might have drawn this incorrectly. So what we're going to compare is the position of our H's and our position of everything else. So from the perspective of this double bond, are the carbon groups on opposite sides or the same side? They're on opposite sides, so we have drawn trans. Let's draw cis. What that would entail would basically be recreating this side of the double bond. And then instead of the carbon number 5 and 6 being up from here, they would be down like that. And the other hydrogen would be there. So we've essentially rotated this group so that it's down instead of up. And so we still have our 6, but this one would be cis. It would still be cis. It would still be 3-hexene, 2-methyl, but it would be cis instead of trans. All right, let's take a look at this one. So this one here, trying to remember, for ring structures that have alkenes in them, there isn't the same thing as cis or trans, so we don't have to worry about that. Okay, so this is 1, 2, 3, 4, 5. So cyclopentene, right? Cyclopentene. Now we have a few places that we can number. We can start numbering here, start numbering here, start numbering here. And the idea would be to get the lowest numbers all the way around. So if we numbered here, it'd be 1, 2, 3, 4, 5. If we started up here, it'd be 1, and then we could pick a direction. Let's say 2, 3, 4, 5. That doesn't seem like that's the best because it's got the largest number for that last group. We could also start here and go 1, 2, 3, 4, 5. Okay, now is there any benefit to having the number 1 over here versus over here? Yes. If we have the number 1 over here, then we've only got one substituent on the number 1, and then the next one is 2 and 3. But if we number going this way, the number 1 actually accounts for this substituent and for the beginning of our double bond. So it covers 2 of our substituents, and then we just have to number a third one. So, yeah. So we're going to say 1, 2, 3, 4, 5. And this is 1 cyclopentene. In fact, I should probably have said that earlier. Let's always make the double bond part of the number 1 carbon in our cycloalkanes, or cycloalkenes. So 1 cyclopentene. Now we have 2 substituents, both of which are methyls. So we can say 1, 3, 1, 3 dimethyl, 1 cyclopentene. 1, 3 dimethyl because of the 2 groups. 1 cyclopentene because we have to say where the double bond is. The double bond could have been here. It could have been down here. So we always want to specify that. All right. Let's talk about the cycloalkenes, since I just showed you one. So to name these, like we just did, we're going to number the carbon atoms on the ring of the double bond number 1 and 2. And so we'll go in whatever direction gets us to a substituent first. So we won't go 1 and 2 this way because it takes too long to get to this substituent. So 1 and 2 this way, and then we're there by number 4. 1 and 2 this way because there's a substituent on number 3. And then everything else is the same. The substituents get listed in their alphabetical order. You don't always have to explicitly say the number of a double bond in cycloalkanes because often it's always going to be on the number 1. So in these examples right here, you see that it doesn't say 3-methyl 1 cyclopentene, right? It's implied that the 1 is going to be in there. So we could have left that out in our previous example of 1,3-dimethyl cyclopentene. Same thing here. 4-ethyl, 1-methyl cyclohexene. They're not saying 4-ethyl, 1-methyl, 1-cyclohexene. Okay. So we can leave it off unless there's more than one, and then we might have to talk about that. There are sometimes alkanes and cycloalkanes that contain more than one double bond, and these are called alkadienes. Alkadienes or alkatrienes, and so forth. So those that contain several double bonds are referred to more generally as just polyenes, Greek for many. So you can see some examples here. 1,3-cyclopentadiene, right? Cyclopentane, cyclopentene, cyclopentadiene. So that's the evolution of that name. Again, this is just as an example. Let's talk about some physical properties. Alkenes and alkynes are nonpolar, means they don't mix well with polar solvents. The only attractive forces between these are what we would call dispersion forces. So you got to remember back to your intermolecular forces. This is the weakest of them. Their physical properties are similar to those of alkanes with the same carbon skeleton. So similar to alkanes. Alkenes and alkynes are insoluble in water, but soluble in one another and in nonpolar organic liquids. Organics. And then alkenes and alkynes that are liquid or solid at room temperature, they tend to have densities that are less than 1, meaning you'll all float down here. They float on water. Sorry, before we go on to the reactions of alkenes, just take a second. Physical properties, similar to alkanes, so you got to remember the boiling points and melting points go up as the chains get longer. They tend to have, the low molecular weight ones tend to be gases, and then higher ones liquids, and much, much bigger ones solids, and so on. I don't know if there's any real solid alkenes that I know of to talk to you about. Okay, let's talk about the reactions of alkenes. Most alkene reactions, let's actually back up a second. We're going to go through each of these individually. Okay, these are the characteristic reactions here. I'm going to go through each type, so like addition reaction, substitution reaction, and so on, addition of HX and whatnot. But these are them at a glance. So for our alkenes, most of them are going to be addition reactions, so that's something that we can know, as opposed to substitution reactions, which would involve switching places with some group, or removing groups. This is addition of a group. And there's a few different ways that we're going to do this to our double bonds. We're going to add what we'll call a halogenation. So in the form of a hydro halogenation. So hydrochlorination, hydrobromination, hydrofluorination, any halogen would work here. Then we have what we'll call the addition of water, which is going to be hydration, adding a water molecule. And pay attention to what is being added. These are going to be binary molecules that are being added to a compound that's going to take 2 new bonds. So both of these parts of the molecule are going to add on to the 2 carbons of our double bonds. Okay, everything here is following that trend. Break H2O into HOH, and you see your 2 parts, Br and Br, whether that's Cl2 or F2, same thing. And then hydrogenation is literally just adding hydrogens. This is what we call reduction or saturation. We'll resaturate these unsaturated alkanes. Okay. The first reaction that we're going to look at, most reactions that we're going to look at are exothermic. So I want to mention that. They do release heat. And this just means that the products are more stable than the reactants. And that's what happens when we have things that are lower in energy after a reaction than they were in the previous to the reaction. That change in energy gets released, and here we experience that as a change in temperature of the surroundings, so it releases heat. Just because they're exothermic, though, doesn't mean that alkene addition reactions occur rapidly. The reaction rate depends on the activation energy, and many alkene addition reactions do require a catalyst to make them go faster, but we're not going to get into the kinetics of that here. Now, this is just an example so you can see what bonds are going to break, what new bonds are going to form. Okay, so there is 3 bonds here, the single and the 2 double, and then we're going to get 3 single at the, 1 double with 2 pairs of shared electrons in it, and 1 single with 1 pair. So 2 pair of electrons, 1 pair of electrons, and 3 single bonds are 3 pairs of electrons. So it all balances out. Okay, the addition of hydrohalogenation, where X here could be a chlorine, a bromine, or an iodine, to give an alkene, gives us a haloalkane. So alkene into haloalkane. So hydrogen adds to 1 carbon of the carbon-carbon double bond, and X, which is, again, a halogen, adds to the other. And so you can see that shown here. Now this reaction is what we call regioselective. That means one direction of bond forming or bond breaking occurs in preference to all other directions, and we're going to follow something called Markovnikov's rule. Markovnikov's rule says that hydrogens are going to add to the less substituted carbon, and that X here, or our halogen, will add to the more substituted carbon. What does that mean? That means hydrogens are going to go wherever the hydrogens are. So hydrogens go to where more hydrogens. Let's take a look. So here we have propene. We have 2 carbons, carbon number 1 and carbon number 2. Carbon number 1 has 2 hydrogens on it. Carbon number 2 has 1 hydrogen on it. This hydrogen is going to go to where there's more hydrogens. That's what Markovnikov's rule says. It also says that the halogen will go to the more substituted carbon. Carbon number 2 is more substituted because carbon number 2 has 2 carbons on it, whereas carbon number 1 only has 1 carbon on it. So that's why the Cl goes to the middle carbon and not to the end carbon. Or another way of saying it, that's why the hydrogen goes to the end and not to the middle. That's Markovnikov's rule. It's going to be the same when we add water for the hydroxide. The hydroxide here will act just like our X, okay? Just like what the chlorine or the bromine or the other halogens are doing. Now, chemists account for the addition of HX to an alkene by a 2-step reaction mechanism. And we like to show curved arrows to show the repositioning of electron pairs during the reaction. We like to show the tail of the arrow at the origin of the electrons and the arrow head showing where it's going, the new position. Curved arrows show us which bonds break and which ones are new or which ones form new bonds. And so I want to talk about the common mechanism step for addition of an HX or a hydrohalogenation. So the first step is what we would call adding a proton. So this is where an acid, for example, is a proton donor, and a base is a proton acceptor. You may remember that from acid-base chemistry. And so most catalysts that happen in organic chemistry are acid-base catalysts. That's a good way of saying it. They're either going to be proton donors or proton acceptors, and that helps ready the molecule for the reaction. Now, in this example here, you can see that how proton transfer happens. So you can see here that to show how we're going to add a proton, the electrons here reach out and grab this hydrogen, basically forming a bond, which we see over here. And then the electrons that are already in this bond come out, and we see hanging out on top of the oxygen after the reaction, right? So this is before, this is after. And so in pattern 1, we tend to see add a proton. There's also another one, pattern 2, which is remove a proton, okay? And so add a proton looks just like what happened here. Remove a proton looks just like what happened here, okay? So this is an example that kind of knocks two birds out with one stone. It's the reverse. And we could do the same thing. We could reverse that and say this guy's now going to reach out with its electrons and grab this one, and then this guy's going to pop back in, and we then reverse this whole thing back this way. And so the adding and the donating and the taking away are now reversed. Okay, here the proton donor was the acetic acid. In the backwards reaction here, the ammonium is the proton donor. This is actually the conjugate acid. This is the conjugate base, if you remember that stuff. There's another mechanism step, pattern 3, and this is what we call electrophile and nucleophiles. An electrophile is an electron poor species. And so they want electrons. They're seeking electrons. They're electrophile, electron lover. They're after electrons. Nucleophile is an electron-rich species. It's got a lot of electrons. It's looking for a nucleus, a positive charge. These are the other mechanism steps. If it's not proton donating or proton accepting, then we see often electrophile and nucleophile. We say something like electrophilic attack, or this chlorine performs a nucleophilic attack on the carbonyl or the carbocation in this compound. And so usually we can see this with charges, pluses and minuses. Electrophile is going to be positively charged. Nucleophiles will be negatively charged. And pattern 4 would be a reaction of a proton donor with a carbon-carbon double bond to form a new covalent bond. So this is going to be kind of what we're seeing, which is going to happen in some reactions that we do. So, for example, here, the double bond provides both the electrons that form the new covalent bond. So it's providing the electrons, so it's acting like, what am I trying to say? If it's not really, so it's kind of like the nucleophile. It's acting like a nucleophile, kind of, because it's got electron density that's looking for a nucleus. And then we also show that that it's a proton acceptor, okay? And so I'm showing you ways that we recognize or we show mechanism steps. And so while this equation here might be the most accurate way to show this proton transfer, which is to show the water molecule, to show the little arrow moving, to show that the bond now changes and the lone pair now is sitting on the oxygen, all that stuff. We often simplify things and just show free protons floating around in space. I'm just trying to show you that in the future, when I'm showing you the mechanism to, let's say, the real reaction that we just did, the hydrohalogenation, it'll look more like this. We're not going to show all of the details, like showing the hydronium ion as opposed to showing just the hydrogen ion. But this is typically what reaction mechanisms look like, involving proton donors, proton acceptors, electrophiles, nucleophiles, and such so on. But you can see in this reaction up here, this is like a two-stepper. By reacting here, being a proton acceptor, it becomes a good electrophile, which now will allow it to go under a nucleophilic attack by something like a Cl minus, that's floating around. And so that's why there's usually some mechanism that we're going to kind of look at. I don't want you guys to worry too much about mechanisms because it's hard for me to test you on that, given that we're going to do Canvas exams that are online, multiple choice and such. Okay, so let's look at the actual mechanism for the addition of HCl to butene here. So the first step is to add a proton. Reaction of the carbon-carbon double bond with the proton gives a secondary carbocation intermediate. Secondary because this carbocation, the plus charge, is on a carbon that's connected to two other carbons. And we can also call a carbocation intermediate a species that contains a carbon atom with 3 bonds to it and a positive charge. So anytime we have a carbon atom, even back in this example here, right? This carbon had this hydrogen, this carbon, but nothing else. And so it has a positive charge. That is a carbocation. So the first step is that we gain this hydrogen, or the hydrogen adds to the double bond. Okay. Notice that the hydrogen here is adding to one side of the double bond only. And here it doesn't matter. This is a symmetrical molecule. So this carbon is literally the same as this one. So we just get a hydrogen adding on there somewhere. So this takes place in 2 steps. The first step creates the carbocation intermediate. The second step is a reaction of an electrophile and a nucleophile to form this new bond. Now remember, the electrophile loves electrons. That's this guy. And the nucleophile is looking for positive charge. That's this guy. And so this reaction of the carbocation intermediate with the chloride ion then completes the reaction. So that's the mechanism. Now, what you will have to do test-wise is I may give you something to react together to test that you know how to react them, but then you're going to have to give me the name of that product. So you need to work on the naming, but you can see how that's going to help me know if you drew the right structure, because if you connect these wrong, you're going to give me a weird name. All right, let's look at the addition of water. So first step here is going to be, wait a minute. Hold on a second. Yep, sorry. Yep, yeah. So I wanted to give you the term for this. So hydrohalogenation was the first one. This one is called hydration. Adding a water hydrates you. Hydration is acid catalyzed. So you'll notice that all of these are catalyzed by our H2SO4. This is a strong acid catalyst. Hydration also follows the Markovnikov rule, which means we're going to add H's to the less substituted and OH's to the more substituted. And you can see some examples here. So in our 2-carbon ethylene, there's no difference. So the OH can literally go anywhere. And so we could, but even if we drew OH here and H here, it's the same molecule just flipped around, right? Not the case so much with propene. With propene, there is a specific place the OH will go. Here it'll go to the least substituted, it'll go to the most substituted carbon. So it'll go here. So again, OH and H makes up H2O. And then with our 2-methylpropene, you can see here, now don't worry about the names ethanol, right? We are making alcohols, and so those of you with a keen eye have noticed that we know how to make alcohols now. So when we get to the alcohol chapter, of course, we're going to be able to react alkenes and water to make alcohols and then name them. And then we're going to be able to dehydrate alcohols back into alkenes and name those. It'll get fun. But don't worry about the alcohols at the moment. But you do notice, I hope you notice, we are making alcohols. And again, let's take a look at this 2-methylpropene. So the most substituted carbon out of this one and this one is, of course, the middle one. And so that's where the OH goes. Now, don't take this to mean that 100% of the products are going to be this. No, that's not the case. Markovnikov's rule predicts what we're going to get a majority of. And in some cases, it's an 80% to 20% majority. Some cases, 99% to 1%. But in some cases, it's actually more like 70% to 30%. And while I don't know the exact numbers for this reaction, and they would be different depending on the reagents, this is the majority project. The major product is going to have the OHs on this more substituted group. It does happen where they end up on the least substituted group. It does happen, but we're going to not do that for this class. Let's look at the mechanism very fast. Step 1, add a proton. Protonization. I don't know if that's how you spell it, but if I ask you guys, what is a common first step in reaction mechanisms, you should say something like protonation, or accepting a proton, or somebody donating a proton. Often. Where is that proton coming from? That's what acids do, right? Acid catalyst. By providing protons, these are around. What do they do when they're around? Well, they go and they mess with the double bond. They form carbocation intermediates. Second step, then, is the reaction of an electrophile and the nucleophile, just like we saw before. Electrophile. I was going to say electrophile attacks, but that's not what happens. Electrophile gets attacked. It's the nucleophile that attacks. And in this case, water is a good nucleophile. Look at that. It's got some lone pairs, some unbonded paired up electrons that are just looking for an atom that's missing electrons, like that carbon. And so then we get this, and you can see here that that's not right. This doesn't look right. The whole water molecule is attached, right? Now oxygen has 3 bonds, 1, 2, 3, and now it's got a positive charge. So this is what we call an oxonium ion. So usually what will then happen is we rebalance, we reform our catalyst. So something comes back in and takes away one of those hydrogens, and this could be some HSO4. Actually that's a lie. This is a strong acid, so it probably doesn't do that. But once this gets going, you can probably imagine another molecule of methylene cyclohexane being the one that comes in here and pulls off this hydrogen. Because this was the original molecule that was needing a hydrogen, and now we have our kind of end product here that's a little bit unstable because of all this positive charge and this extra hydrogen, and something just needs to come take that off. It doesn't have to be the leftovers of our acid, of our catalyst. It could be, and it doesn't necessarily have to float off into space like this either. This doesn't happen, by the way. It might have been scooped up by a water molecule. Another water molecule might have, come by and grabbed it. But more likely, another molecule of our reagent or reactant probably did it. All right. And so I should mention it. Add a proton, so lose proton. Deprotonization. Okay. So that's the mechanism. Pretty cool, huh? Let's look at the addition of chlorine and bromine. So this would just be called a halogenation. Not hydrohalogenation, but halogenation. So adding halogens. Now, of course, 2 chlorines and 2 bromines mean we're going to add 2 bromines and 2 chlorines. There's not a lot here to mess up on or go wrong on. These bromines are going to go to both carbons, right? We're going to look at our double bond, see where it is, and go bromine, bromine, or chlorine, chlorine, or fluorine, fluorine. These reactions are generally carried out at room temperature, these addition reactions. They take place readily at room temperature. They're carried out using pure reagents or mixing them in a non-reactive organic solvent so that they can mix with each other without side reactions. The presence of Br2 is actually a really good test to see if we have saturated alkanes. And the reason we can do that is because bromine on its own, I was going to write bromine, is red. But whenever it becomes incorporated into a haloalkane, these things, the color goes away. And so we can add bromine to a jar of hydrocarbons, these are hydrocarbons. And if we add some drops of bromine and we see red color persisting, then that means that these are saturated. That means there's no room for bromines to add on to the molecules, and bromine just stays in here as Br2, which is red. But if the color quickly disappears, then we know that there was some unsaturated or double bonded carbons in there. And those carbons will quickly pick up the BRs. They lose their double bond, and the BR loses its bond, and the red goes away. So we can use that as a test to see if we have a presence of unsaturated alkanes. We're not going to look at a mechanism for that. And for the last reaction, we call it reduction. This is the addition of hydrogen. This is also the saturation reaction. We can turn unsaturated oils into saturated oils by adding hydrogen. This always takes place in the presence of a transition metal catalyst. More commonly, it's palladium or platinum or nickel. And what this does is it reduces the double bond. So the double bonds go away. If we have a double bond here, it goes to single bonds. So butene becomes butane. It doesn't matter if it's trans or cis. Once we get rid of that double bond, rotation is free again, and then this thing just becomes a wiggly chain of connected carbons. And so, yeah, we can do this with cycloalkenes as well. This just reduces to the regular cycloalkane. And I will show you a picture of why we use a catalyst for this. The catalyst, the metal surface actually provides a nice way, a place for the hydrogens to add on to. Yeah, metals are good conductors of electricity, and so the electrons can move very readily, and the hydrogens also like to associate on. So these are hydrogen gas. Usually you bubble hydrogen gas through the liquid alkene. But the hydrogen gas will react with the metal surface, lose electrons to the surface, and then very easily rearrange onto this, the surface of these molecules. Very cool. One last reaction that we're going to talk about for alkenes is polymerization. From the perspective of the organic chemical industry, the single most important reaction of alkenes is the polymerization reactions. So alkenes, because of their nature of having those double bonds that are pretty reactive, means that we can find them or we can take monomers and link them together into what we could call polymers. So a monomer is just Greek for mono meaning single and meros meaning part. So just repeating part or single parts. You can see it here. This is a monomer of, what is this? This would be C double bond C H CH3 H. So this is just propene. 3 carbons in a row. First carbon has the double bond on it. We don't have to say one propene because there's no other way to draw propene. So this is just propene. So I love it. It's over here. Taking propene, which is just a double bonded, simple, small alkene, and linking them together. Let me show you what happens if we take C double bond, C double bond, C double bond, methyl, methyl, methyl. So if I take 3 monomers and I let them react together, what happens is the double bond moves to form just a single bond between them. So this double bond goes away. Now we have a single bond. This double bond goes away, single bond. Double bond goes away, single bond. And we end up with just a straight chain of regular repeating. So every 2 is going to have a methyl sticking up off of it. That's what polymers do. And there's so many different monomers out there that we can link together. So I'm going to show you a list. This is propene though. If you extend propene into a polymer, you get polypropylene. Remember, propylene was that common name. Polypropene is a real name. Polypropylene can be used for lots of different things. So polymers are just many units of a alkene. So here's a couple. You can see here, linking together a bunch of ethylenes gives us polyethylene, or a bunch of propylenes, polypropylene. You can see what they're used for. Polypropylene carpet fibers, polyethylene, break-resistant containers, 1,1-dichloroethylene. So that's C double bond, CLL, CLL, H, right? This is 1,1-dichloroethylene, so 2 carbons, 2 chlorines on the same one. This is saran wrap, but in a repeating unit. So repeating off in all directions. So right, carbon, 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 on and on. But these two carbons have chlorines on them, and on and on and on. Where's another one? Teflon's on here somewhere. Teflon is tetrafluoroethylene. So this one has fluorines replacing all of the hydrogens. Anyways, I just wanted to show you guys the polymerization reaction, show you some of these polymers, go a little bit more in depth on polyethylene just to show you. So polyethylene comes in a few flavors. There's the LDPE, or the low density polyethylene. It's low density, it's highly branched. Polymer chains do not pack well, and so because they don't pack well, they don't get very dense. This softens and actually melts at about 115 degrees, 115 degrees Celsius. Approximately 65% of all LDPE is used for like films and packaging, like trash bags and that kind of stuff. And then there's high density polyethylene. Now this one only has minimal branching. These chains pack together well. The dispersion forces between them are pretty strong. And these have higher melting points. And these can be blow molded into like squeezable jugs and bottles and other type things. Let's see. I think this is high density. Yeah, so this is low density. A lot of films and again, lightweight type plastics. And then the high densities, like for our graduated cylinders, for example. So we get a lot harder of a plastic. And that's really it. So that's about it for this chapter. Now let me look real quick at the post chapter questions just to see if there's anything on here I want you to focus on. Definitely naming. Practice naming and drawing alkenes, cycloalkenes. Don't forget about cis and trans. People tend to forget those. And then predict reaction products. So there's a few questions on here that give you some structures and ask you to predict. Now, I will direct you to a problem like this. Let's say I draw an alkene, and you should do these types of problems. Give yourself an alkene, and then draw what happens when you add HCl, and what happens when you add H2O, and what happens when you add hydrogen gas, and what happens when you add chlorine gas. That way you're counting your hydrohalogenation, your halogenation, your hydration, and your hydrogenation all at once. And I'll just show you very quickly. But I want you to practice these. Don't do them with just so simple ones like this. Practice harder ones. These are too easy because there's no wrong answers. Like, you can't put them on the wrong places. Boom. There we go. But try it again with maybe something like that, or like that. That would be more fun. So do that one. For some of these, remember there are catalysts involved. Don't forget about the mechanisms. Nucleophilic attack after a proton addition, but so carbocations and such like that. I might ask you about those in the quizzes or in the exams, some of the details. But focus on these and being able to not only draw the products but to name them. So pause it, give it a shot. I'm going to write the answers here in a second. All right. So those are your answers. Remember, Markovnikov addition. That's why I went there. Doesn't matter here, right? They're all bromines, and doesn't matter here because they're all hydrogens. But when you're adding a halogen or an OH, Markovnikov addition. Also, practice a little bit with some polymers. Know the definitions. Definitely know the definitions of things like monomer and polymer. You don't need to focus on the details of the different kind of polymers. Um, okay, I think that's it. So this one had some naming, a couple of new terms like alkene, alkyne, diene, triene, polyenes, right? Carbocation, a couple of mechanisms, and a couple reactions. So do your best, and I'll see you guys in the next chapter, chapter 13.